Hello! Okay, today I am going to be doing a test, a hypothesis test, specifically a Chi-Squared GOF fit test, by trying to see if this die right here is fair. So, I've got this camera set up inside a dice tray that can hold it, and I've got one webcam. I turned up the contrast so that the number can be seen very clearly, no matter what. And then over on this side, I've got a note card that I'm going to be tallying up the results. And then afterwards, we will apply a Chi-Squared GOF fit test. Our significance level is going to be an alpha value of 0.05. Our null hypothesis is that the die is going to be fair, so each side of the dice, each face has a 1/6 probability, but the alternative hypothesis is that it's not fair, and we shall see which is correct. So, without further ado, I'm going to get started. All right. I wish I was more of a charismatic person. I don't really know too much what to talk about when I'm doing this. That's 1, 2, 3, that's 3, 5, 6, 7, 8, 9. Actually, no, 8. 9, 3. Our first 5 in anyone's score is 3. It seems like we're getting a lack of 4s. Now 5 in 1. There's a 4. Actually, we're getting a lack of 2s as well, and a lack of 6s. It's really liking 5s, 3s, and 1s. Our second 2. 5. 2. I'm very curious how the dice results will turn out. 3. We currently have 5, 10, 15, 20, 24, 28. 29, 30, 6 finally. 2. Okay, now we're getting a lot of 2s. They're coming. Okay. 5. 6. 4. 5. Reached 10 and 5. So we've got currently 30, 40, 30, 35, 38, 41, 44, 48, 49, 50, 'Already over halfway there. When I was younger, I used to think that like 100 was a really high number. And it's big, but I realized numbers are really how you portray them. A lot of numbers, they can feel big until you just put in like a certain context or use a certain model to display it, and they can look really small, really insignificant. And 100 can look really small a lot of times when you put it in certain ways. And sometimes even just counting. Like you can count to 100 very quickly. Which is really funny. Rolling a lot of fives. 1, 4, 1, 2, 5. Take a second to count it up in just a second. 1. Maybe once I roll another 6, I will. It'll be kind of easy to count it up. 5, 3, 2, another 5. Come on, give me a 6. 5. 4. Another 4. 5. It really doesn't want 6s. Really doesn't like 6s. 5. It's going to give me another set of... Oh, there we go. Okay, count up is going to be... so 30, 60, 70, 74, 78, 80, 85. 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100. Okay, let me make sure. Let me tally it up. So that's 30, 60, 70, 80, 88, 90. Wait, did I count that wrong? Oh, 90, 95. Yep, 100. All right. Here are the full results. You can see the tallies. And now, I'm just going to be right back after I do the calculations, and I will go over them with you. And we're back. So, now I've switched cameras around so you can see all the math. So here I've taped up the entire tallying of all the results, and then I also wrote them out here so you can see they total to 100. Here is our null hypothesis, which is that the die is fair, each face has an equal 1/6 probability. And then our alternative hypothesis is that the dies are not fair, that the null hypothesis is not true. So, in order to do a chi-squared test, we have to make sure that our assumptions are correct. So first, we need to make sure that our sample is large enough that each expected frequency has at least an E of at least 5. So that E is the expected frequency for each category, basically. So, and we, as I can show right here, we have 100 data points. If we divide that by 1/6, we get an expected frequency for each category of 16.67, which is very notable. So what we do, that because 16.67 is greater than 5, we can check off that as assumption is met. Next up is that each observation is independent. Since we're rolling a die 100 times, then every single observation is of course independent, since none of them depend on any other dice roll to be made, or any other result. So that's met. And lastly, that each category is mutually exclusive. You can't roll and have a 1 and a 2 for each observation, so they are mutually exclusive. You can only have a 1, 2, 3, 4. It can only be one of these for every observation. So they are mutually exclusive. Because we meet all of those categories, then we can do the chi-squared test. So chi-squared is equal to summation of, for each category, the observed frequency minus the expected frequency squared over the expected frequency. So I wrote that all out here and summed them all up, and I did the calculation for that. As I can show you, here is the total. I wish there was a faster way to do this. And you can see the entire total for all of them. And when you punch in the result, you get 13/5. As you can see here, wrote that out, which equals 2.6. So I've been writing 16.67, but I used the calculator. That way I could just do 100 over 6 for every single value. I'm glad I did, because then we got a much nicer value of 2.6 instead of having long and weird decimal points. So now we have 2.6. We need to compare that to our critical value using the chi-squared table. So here's the chi-squared table. Because our degrees of freedom, we have 6 categories, or our k is 6 minus 1, so our degrees of freedom is 5. So if we look here on the chi-squared table, you can see right here our critical value is 11.070, which I have written right here. And if we compare that to our value that we got of 2.6, it's pretty clear that 2.6 is much less than 11.070. 0.070. So even though we got a lot of 5s rolled, this overall we fail to reject the null hypothesis, since it is less than the critical value we set. And therefore, the data likely indicates that this die is fair. And yeah, there we have it.